Hello everyone and welcome back to Diksha Karnataka YouTube channel, and you are watching KCET 60 out of 60 in physics series, where I am trying to help you to achieve of your dream of getting 60 out of 60 in your KCET 2025 exam. And if you are following our channel, then obviously you know that we have already completed all the second PU chapters. Currently we are going through first PU chapter revisions. Okay, we have also almost completed all the chapters of your first PU. Today I am going to discuss thermodynamics. Okay, it is one of the important chapter with respect to first PU. Okay, every year at least one question comes from this chapter. Some years two question also comes from this chapter. So you cannot ignore this chapter if you want to score 60 out of 60. And if you don't have enough study of this chapter when you are in first PU, you can skip this chapter. But I suggest that at least go through this lecture at least once and check if you have any doubt. Most of the questions are based on only few concepts from this chapter. So if the concept is within your reach, you can answer it. If it is outside of your reach, you can skip it. But I request you at least watch this video. Also, before starting this video, I request you to join our WhatsApp channel. The link is given in the description. Whenever we are doing something new, you will get an update in our WhatsApp channel. This is a WhatsApp channel, not a WhatsApp group, so your privacy will be completely retained. No one will know your phone number or anything like that. Okay, it will be only our communication channel. So whenever we are posting a video or we want to take your opinion on, then only you can check from this channel. Also, if you are watching this video for the first time, I request you to subscribe to our channel. So let's start with today's topic list. What all we are going to discuss. Don't afraid, we are not going to discuss every detail, every theory from these concepts. We are only going to discuss the important gist of every concept, so that you are ready for your KCET exam, right? So first we are going to discuss thermal equilibrium and zeroth law. Then we will discuss first law of thermodynamics. Then we will discuss specific heat capacity. We have discussed about heat capacity in our previous chapter, but that was general heat capacity. This is specific heat capacity for gases only. Okay, then we will discuss about thermodynamic processes. Few thermodynamic processes are very important. Then we will discuss second law of thermodynamics. Okay, and last but not the least, the most important concept from this chapter is Carnot's law. Okay, if you take at least last few years questions, out of 10 questions, 5 or 6 will be from this Carnot engine concept, Carnot's engine concept only, right? So Carnot's engine is very, very important. Okay, it is not directly always using single formula. We will see one or two examples during our lecture, but tomorrow we are going to discuss the PYQs. I have not combined PYQs in today's lecture. This chapter is considered a little bit heavy for students, so PYQ I have kept separately. Okay, so let's start with the chapter. First, let us look into thermal equilibrium and zeroth law. So what is the zeroth law? Two systems in thermal equilibrium with the third system separately are in thermal equilibrium with each other. So let us understand this meaning of this thing completely. So we have here two systems, A and B. Okay, and they are insulated from each other. They do not have any contact between them. They are insulated from each other. So the red line marks that they do not have any contact. Okay, this is completely isolated. A and B completely isolated. And here you have something which is a third system which has a contact with this. Okay, so this is in contact. They can exchange heat from here. Okay, we already learned a little bit about heat in our previous lecture, not yesterday, previous lecture, right? So here what we are doing, we can understand that this system can exchange heat with C. Similarly, this system can also exchange heat with C. Now once they are exchanging the heat, then we cannot call them at equilibrium. What is the meaning of equilibrium? So if you remember, in case of kinematics, we learned that equilibrium means object is moving with either constant speed or it is in a static condition. right? In rotational equilibrium means when the object there is no external torque acting on the system, we call it rotational equilibrium. In kinematics it was when the no external force is acting on the system, we call it kinematical equilibrium. Okay, it can be either constant speed or it can be either static. Obviously, similarly in case of rotational motion, the equilibrium means no external torque is acting on the system. Now, what is the meaning of thermal equilibrium? Thermal equilibrium is slightly different. In this case, in case of thermal equilibrium, no heat is exchanged. Okay, when the amount of heat exchanged is 0, okay, so if there is no exchange of heat between two systems, then we say this system is in thermal equilibrium. Okay, when there are no exchange of heats, if there is no exchange of heat, then we say this system is in thermal equilibrium. Okay, now if A and C are in equilibrium and B and C are in equilibrium, then the zeroth law states that these two systems individually will be also in equilibrium between themselves. Okay, so if you replace this insulating medium with a conducting medium, then they also will not exchange any heat. Okay, now why this is called a zeroth law? There is a good story. I know most of you know that because first law and second law of thermodynamics was created much earlier than this law, and once this law was discovered by Fowler, he realized that this law is more fundamental compared to first law and second law. That's why it was termed as zeroth law. That was the reason why it is called zeroth law. In any case, any other laws, you will not find anything called zeroth law. For example, Newton's first law, Newton's second law, Newton's third law, but there is nothing called Newton's zeroth law. Right? For thermodynamics, because of the nomenclature, because it was already discovered and it was already published widely across the world, that first law of thermodynamics states that. Okay, second law of thermodynamics states that. So that's why when this law was discovered, then they realized, scientists, physicists, they realized this is much more fundamental compared to first law of thermodynamics. So it should come first in the order, but it was discovered last in the order. Okay, that's why it is called zeroth law of thermodynamics. Okay, now one more thing, when two systems are in equilibrium, what is the condition for two systems to be in equilibrium? Obviously they are not exchanging any heat, but what else? When two systems will not exchange any heat? So two systems will not exchange any heat when their temperatures are same. So suppose this object has a temperature, say T1. Then if A and B are in equilibrium, then this object will also have the same temperature T1, and by that logic we can say that this object will also have the same temperature T1. Okay, so they all will have the same temperature, and common language we can say all the temperatures are T. Okay, I hope it is visible. If it is not, let me make it a little bolder. Okay, so they all have the same temperature. So when two objects have same temperature, they do not exchange any heat energy. So basically this law gives the definition of temperature. Okay, zeroth law. From zeroth law we are getting the basic definition of temperature. Okay, temperature is when two objects are in thermal equilibrium. The quantity which defines that thermal equilibrium is basically the temperature. Okay, so temperature is same for all these objects, right? So first law of thermodynamics, zeroth law of thermodynamics gives the definition of temperature, and it says that if two objects are in equilibrium with a third object, then individually, then these two objects will also be in thermal equilibrium. Okay, now let's move on to the next concept. First law of thermodynamics, very important thing to remember. What is the statement? The energy supplied to the system goes in partly to increase the internal energy of the system, and the rest in the work on the environment, delta W. So if you supply, suppose you have a system. Okay, I will first, let me explain a little bit, then I will try to explain with the real life example as well. So if you supply some energy to the system, some energy, say delta Q, to the system, okay, then what happens to this energy? First, some part of the energy is directly absorbed by the gas, which increases its internal energy. Okay, so internal energy is increased, some part is consumed by the system, that is internal energy, and rest of the energy is converted into work by the system. So system does some work on the environment, okay. So that work is delta W, and if you supply delta Q energy, some energy is absorbed by the system, delta U, and rest of the energy is converted into work. So for example, if you go to a shop and if you buy, suppose, a 10 rupee chocolate, okay, you will see the bill. If you see the bill, you will realize that out of the 10 rupee, the cost of that product is only 8.2 rupees. Okay, you will show that it will show you to you that the cost of the chocolate is 8.2 rupees, whereas 1.8 rupee is going towards as taxes. Okay, so 1.8 rupee is going towards the taxes that is claimed by the government. Okay, so basically what you are doing, if you pay 10 rupees to buy the chocolate, okay, 1.8 rupees taken by the government, and you are getting 8.2 rupee valued chocolate. Okay, so you can understand. So whenever you wanted to do something, some part is taken by the system. Okay, some part is taken by the system as in form of taxes, some cases in form of bribes, in some cases in as form of profit as well. So whatever money you are spending, you are not getting the exact amount of value in return. Okay, that is the nature. That is not only the nature of human being, that is also nature of nature, right? So that is also, nature also likes to keep something with him, okay, with it. Okay, in some cases nature do not keep any internal energy change is zero. So in case whatever heat you supply, the same amount of heat is converted into work. There are certain cases. We will discuss that in later later part if you want. Okay, not today. Today we are only focused on KCET syllabus. Okay, those parts are important in your first PU as well as in NEET and JEE, but not in KCET. KCET, those concepts are not required. Only the basic formula of thermodynamics is sufficient, right? Now what is the law? Basically, if you supply delta Q of amount of energy, okay, delta U is the increase in the internal energy, and delta W is the work done on the system. Okay, work done by the system on the environment. Okay, now this work done can be represented using delta W is equal to P delta V. Okay, so if system undergoes a change, what is the value of this work done? This work done can be represented using P delta V. P is the pressure of the system, delta V is the change in the volume. If the change in volume is 0, then work done is 0. Okay, if volume does not change, then work done is not change. And in terms of integration, the total work done can be calculated using integration of between initial state to the final state. There will be some values. Okay, so at some constant temperature, constant pressure, say 10 atmospheric pressure, okay, volume changes from 1 liter to 2 liter. What is the work done? So you have to calculate the value. So this is the initial condition, this is the final condition, okay, and if you integrate it, you will get the value of work done. Okay, now based on the what type of process it is, P can be constant, it may not be constant. Okay, if P is not constant, then you have to input the values of it, and then you have to calculate do the integration. I hope you remember it in your from your first PU. Okay, the adiabatic work done, isothermal work done, you have done that kind of calculations, right? So that's how you can calculate. So this is the formula for work done. Okay, now area under, what is important is that it is an integration. Integration means if you know the graph, if you know the plot of P versus V, then the area under PV graph gives you the work done by the gas. Okay, so if you can calculate the area under PV graph, then you can calculate the work done by the graph. So suppose you have a PV graph, V is in this direction, P is in this direction. Okay, so you have this kind of process. So if you take, this is, suppose this is the P and this is the delta V. Okay, so P delta V, if you do that for all such small portions, okay, and then you add them, then you will get the total work done, right? This is the integration by definition, right? So if you know PV graph, if you calculate the area under the graph, you can find the work done in that process. Okay, Apart from that, this first law of thermodynamics is also a direct consequence of conservation of energy. Okay, you should know that the first law of thermodynamics is a direct consequence of conservation of energy. Sometimes this is directly called as conservation of energy principle. Okay, because energy cannot be destroyed or created, so whatever energy you will supply, this is the supplied energy, this is the received energy by for you, and whatever energy is left, that is being absorbed by the system, so energy is not getting wasted. Okay, so energy is not getting wasted, so you can say this is directly a conservation of energy principle, or you can say this is a consequence of conservation of energy principle. Because energy is conserved, whatever energy you supply, that energy has to be either converted into work or converted into internal energy, or it can be both. Okay, now let's move on. See one problem. 1 mole of ideal monoatomic gas is taken around a cyclic process MNOM, the work done by the gas. So here a cyclic process MNOM. So this is the cyclic process, and they asked you calculate the work done. Now what is the rule we just learned about the work done? So this is a PV graph. If we can calculate the area of this region, that will give us the work done. Right, so area under PV graph means whatever closed area it is there. If it is a closed area, obviously this is the, if you have to find this area. Okay, if it is not closed, suppose this is on the x-axis, then you have to calculate, you have to include the x-axis as well, but in this case this is a closed process, okay, cyclic process, so only this area is sufficient for you to calculate the work done. Now how to calculate work done? This is a, what is the shape of this? The shape of this is a triangle. So triangle, what is the area of a triangle? Triangle's area is half base into height. Right, so what is the base here? So this is basically the work done. So work done is area is work done, and area is half base into height. So what is base? In this case base is this. Okay, so this is the base. So ON is the base. ON is the base. So its final value is 3V and initial value is V. Okay, so V naught, actually 3V naught minus V naught. So this is the base. Okay, so this is the base, and height is again 3P naught minus P naught. Right, this is the height. So final value minus initial value. So this is the area. So this is the work done, half times 2V naught times 2P naught. Okay, so one of the half will cancel, so it will be 2P naught V naught. Okay, so the answer is 2P naught V naught. Okay, it came in 2024. Simple question. Okay, that's why I said you should learn this chapter, you should go through this chapter at least once. If the question is easy, you can answer it. Okay, in 2023 the question level was slightly difficult, and it was not super easy to solve, but it was not too difficult also, but it was over average it was difficult compared to other questions that came in this year. We will see that everything tomorrow. Okay, so this is an easy question, came in 2024, so if you know this, you can calculate it easily. Okay, now next question, next part, specific heat capacity. What is specific heat capacity? Let's see what is the definition. So we learned that yesterday specific heat capacity is heat supplied divided by the increase in temperature. Now in case of previous chapter, we generally denoted specific heat capacity with the symbol S. From this chapter we will denote this with symbol C. Okay, and specific heat for 1 mole of gas is generally defined by 1 by N delta Q by delta T. So one of them is capital C, one of them is small c, so it is very confusing. Okay, but you can also remember this molar heat capacity. This is called molar heat capacity. Okay, if you know the number of moles, you just need to divide it by the specific heat capacity, that's it. Okay, but the most important part from this chapter is specific heat capacity at constant pressure. Okay, so there are some cases where you can calculate delta Q from first law, okay, and delta T from the gas equation, and if you put them at constant pressure, okay, there are different equations for that, you remember. So this is called specific heat capacity at constant pressure, and specific heat capacity as constant volume is given by delta T constant B. Okay, now if you remember, why do we need two specific heat capacities for gases? Okay, we do not need two specific heat capacities for solids or liquids. Okay, only for gases we need two specific heat capacities. Why? Because if you keep the when you increase the temperature of a system, okay, you have a gas in a container. Okay, you have a container in a system, and if you want to keep that gas in the same volume, and if you increase the temperature of the gas, then its pressure increases. Okay, similarly, if you want to keep the object at the same pressure, okay, then you have to allow it to expand, so its volume increases. Okay, in all other cases only volume increases, pressure does not change. Okay, so for solids, for liquids, only volume expansion is important. Volume expansion, linear expansion, so everything is related to physical dimensions, right? But pressure, we assume it is almost constant. Okay, very small change happens, so Cp is practically zero for solids and liquids. Okay, but for gases you cannot ignore that, because gases are so far apart. So when you are heating it, not only it's you can increase the temperature by keeping volume constant, you can also increase the temperature by keeping the pressure constant as well. Okay, so in both cases different amount of heat is required, so that's why two different heat capacities is there. Okay, and they are not same, nowhere they are same. As you can see, Cp minus Cv for a gas, for n mole of gas, it is given by Nr. R is the gas constant, right? For 1 mole of gas, this becomes Cp minus Cv equals to R, right? Now what else? One more thing that you have to remember, that there is a ratio of specific heat capacities, gamma equals to Cp by Cv. We will learn more about gamma in our next chapter. Okay, kinetic theory of gases, there we will learn more about gamma. But what is gamma? You should remember, gamma is Cp by Cv. Okay, so this is the basically the ratio of these two heat constants. Okay, and it is generally greater than 1, and greater than 1 means Cp is always greater than Cv. Okay, you can see that Cp is always greater than Cv, and based on what gas you are choosing, they will give you different values of gamma. Cp minus Cv is constant, okay, but gamma value can change based on what type of gas, monoatomic gas or diatomic gas or triatomic gas. We will learn about that in our next chapter class. I am not going to discuss in detail about it, but this variable required to be declared here, because we will see some expression related to that. Okay, so what is the expression we are talking about? We are talking about different thermodynamic processes. So what are different processes? There are mainly 4 important processes. First is isothermal process. In isothermal process, so process means, what is the meaning of process? First let us understand what is the meaning of process. Okay, process means whenever you are heating a gas, okay, or you are changing something in a gas, you have a container full of gas and you are doing something, some experiment with this gas, then that is called a process. Okay, this kind of process is very common, and we will see in our last part, Carnot engine, there we are using different processes, and I will also give you a real example where that kind of process you can see. Okay, so there are basically 4 processes, and most processes are ideal processes. Okay, in practical single process, every process turns out to be only one process. But for example, isothermal process is where temperature is constant. It is very difficult to achieve. It is a almost ideal process. Okay, so here what happens is the temperature remains constant, so you are heating some object. Suppose you have a gas. Okay, you have a gas, and if you heat this gas, what will happen? You try to keep its temperature constant. Whatever, no matter whatever heat you are giving, its temperature will remain constant, right? So the gas will expand very slowly. So it is a very slow process. Very slow process. Okay, another name for slow process is quasi-static process. Quasi-static process is nothing new process. It's just a undergoing changes at a very slow rate. That is called quasi-static process. Okay, so the isothermal process is basically when everything happens in constant temperature, and in isothermal process PV equals to constant. Okay, for isothermal process PV equals to constant. There is one more process which is called isobaric process. In isobaric process, what happens? Bar means what? Bar means pressure. So iso means constant. Okay, you should remember this meaning of this. Iso means constant. Okay, isothermal means temperature is constant. Okay, isobar means pressure is constant. One term for pressure is bar. Okay, that's why this name came baric. Okay, isobaric. Isobaric means constant pressure. Isochoric, core means volume. Okay, so isochoric means constant volume. Okay, if the volume is constant, then it is called isochoric process. And most importantly, adiabatic process. Adiabatic process is very quick, very fast process where no heat is exchanged with the surrounding. So if you take a system, okay, and if you heat it, but if you keep it away from everything by insulating it from the surrounding, okay, then you call this process as adiabatic process. Okay, for example, I am talking here. Okay, my sound energy is traveling from here to the recording device. So that traveling sound, and you are hearing it from the mobile or laptop to your ear. The process through which the sound travels is an adiabatic process. Okay, sound travels in an adiabatic process. And in case of adiabatic process, PV to the power gamma equals to constant. Okay, what is gamma? We already learned that gamma is Cp by Cv. So in case of adiabatic process, PV to the power gamma equals to constant. Okay, and based on this, lot of question comes in JEE advanced level exam. Okay, so but we are not going to discuss that here. We are mainly focused for KCET exam, right? So now let's move on to the next part, second law of thermodynamics. This is also very, very important. What is that? So there are two statements about second law of thermodynamics. In first law of thermodynamics, there is only one statement, delta Q is equal to delta U plus delta W. So if you supply some heat is getting converted into internal energy, and rest of the energy is converted into work. Right? Now in case of second law of thermodynamics, there are two statements. One is called Kelvin-Planck statement. Another is called Clausius-Clapeyron statement, or simply Clausius statement. Okay, so Kelvin and Planck, Max Planck, they are both very famous people in physics. If you get some time, read about them. Okay, so first, what is Kelvin-Planck statement? No process is possible whose sole result is the absorption of heat from a reservoir and complete conversion of the heat into work. So what is the meaning of reservoir? Reservoir, I hope you know the term. Okay, we have water reservoir in our homes, right? So what is the meaning of reservoir? Reservoir means when you take the water from it, its height barely changes. Okay, so it has a lot of storage water. Okay, and ideal reservoir means it has infinite amount of water. Okay, like a sea. Okay, so ideal sea is a reservoir of water. It has unlimited amount of water. If you take one bucket from the sea level will not change, right? So because it has a very huge amount of water. So similarly, okay, in case of thermodynamics, if I say reservoir means it's a source of heat which has unlimited supply of energy and at constant temperature. Okay, its temperature is generally constant and it has an unlimited source of heat. Okay, for example, your gas stove is a source of energy. It provides temperature, almost the flame temperature is almost constant. Okay, so you can consider your gas flame is a reservoir. Okay, heat reservoir, or your candle flame also. Candle flame, you can also consider that to be a reservoir. Okay, now what is the meaning of this thing? So meaning of this thing, suppose we have a reservoir is generally drawn like this, like your water reservoir. Okay, so you have a water reservoir, so this is like where you store the water. So this is a reservoir, and if we have a device, okay, if you have a device which is taking heat energy from this system, okay, and convert the entire heat energy into work. This is not possible. So it is saying that this is not possible. So you cannot expect anything to be 100% perfect. So this is the basic meaning. I hope many one of you are laughing and you are thinking, okay sir, you are correct. Yes, so it is says that you cannot convert 100% of the heat energy you absorb from a reservoir and convert into work, right? So if you want to score 60 out of 60 in KCET, and if you think I will study only 60 questions and I will get 60, okay, second law of thermodynamics says no, it is not possible, bae. You have to study at least 600 1000 questions to get 60 questions correct, right? So it is the limitation put forwarded by not me but by second law of thermodynamics, right? So second law of thermodynamics says that you cannot achieve 100% result if you are only doing 100% work. Okay, so if you want to achieve 100% result, you have to work 300%. Okay, then only you can achieve 100%. Okay, clear? So Kelvin Planck statement says that you cannot take heat energy from a reservoir and convert every ounce of the energy you take it into the useful work. So that is not possible, right? So what will happen? It will release some. It has to release some heat back to the another object which is called. So this is reservoir. This is called sink. Okay, so whatever energy you absorb, some part of the energy will be rejected. Okay, suppose Q1 energy is absorbed, then Q2 energy is released, then rest of the energy can be converted into work. Okay, so basically this is the meaning of that. So work done is basically difference between the energy you absorbed and energy you released. Okay, so suppose you absorb say 10 joule energy and you reject say 2 joules of energy, then work done is 8 joules. Okay, so in Mota words, what we can say that you study for 8 hours, you remember say 6 hours of study, 2 hours you are distracted and you do not remember whatever you have studied in that 2 hours, like that, right? So now next is Clausius statement. What is Clausius statement? No process is possible whose sole result is the transfer of heat from a colder object to a hotter object. Okay, so it says that no process is possible whose sole result is to transfer of the heat from colder object to hotter object. So basically now what is it saying that we have, suppose we have a colder object here, we have a hotter object here. Okay, you cannot transfer, obviously you cannot transfer energy from colder object to hotter object. Okay, to achieve that, what you have to do, you have to do some external work in the system. If you do some external work into the system, then you can take energy from colder object, heat from colder object, and you can transfer it to the hotter object. Okay, so now these two laws are necessary. Why do we need two laws for second law? This law is for engines. Okay, this is called engine law. Okay, all the engines that we use in our life, okay, so starting from motorcycle engine, bike engine, car engine, okay, the engine that is working in your home to lift the pump, to store the power when there is a power cut, okay, we call it generator. Okay, so that is also included an engine. So everything is basically based on Kelvin Planck statement. Okay, so this is called engine law. And Clausius statement, so as you have guessed correctly, this is based on refrigerator law. Okay, this is called refrigerator law. All the refrigerators in the universe, that works on the principle of Clausius statement. Okay, so what is the duty of a refrigerator? Refrigerator keeps cool inside, right? So it takes more heat energy from inside and it transfers that energy to the surrounding, which is much hotter compared to the refrigerator, right? So it always, what it is doing, it is taking heat from inside and and supplying it to the outside. So Clausius statement says that that is not possible by any system unless you are doing some external work. That's why you require the power supply. Okay, you require the power supply so that this Clausius statement is possible. So the power supply is actually providing the work done required so that the energy can be transferred from the inside to outside. Okay, so that inside remains cool. Okay, so I hope everything is clear. Now we are going to discuss about the most important concept from this chapter, which is Carnot's engine. Okay, so what is Carnot's engine? A reversible heat engine, okay, operating between two temperatures is called a Carnot engine. So first let us understand what is the meaning of reversible. Okay, so reversible, I know many of you have seen a car. Okay, so you can drive the car in the forward way, you can drive the car in the backward way also, but when you are moving in the forward direction you can move with a very high speed, but when you are moving in the backward direction, same engine drives it very slowly. But if it is an ideal reversible engine, then the way you are moving in the forward direction, the same way you can move in the backward direction. Okay, so reversible engine means if you can operate it forward direction, you can operate it in the backward direction as well. Okay, that is called a reversible engine. Okay, so now this is a reversible engine. Carnot's engine is an ideal engine. Okay, it is not a practical engine. Okay, all the other engines have less efficiency compared to Carnot engine. Okay, Carnot engines also are not 100% efficient. These are the very important points for your KCET and for your objective questions. Okay, you have to remember that Carnot engines are not 100% efficient. What is the meaning of efficiency? We know that if I give you 100 joules of energy, okay, then if you can convert entire 100 joules of energy into work, then we say this is 100% efficient. But that is not possible by the second law of thermodynamics. Second law of thermodynamics says that if you are receiving 100 joules of energy, you cannot convert the entire energy into work. You have to waste some of the energy, right? You have to waste some of the energy and you have to send that back to the sink. So if you send that, say 10 joules of energy to the sink, then only 90 joules of energy you can convert into work. Okay, so Carnot engine is an engine which can convert energy into work, but it also rejects some heat to the back to the sink. Okay, now the efficiency of Carnot engine depends on the temperatures on which temperature difference between which it is working. Okay, and all heat engine basically has something which is very common, that they are operating between two temperatures. Okay, I will explain it in a while. Okay, so what is the meaning of that? You have a source. You have a source, say at temperature T1. Okay, you have a source which is working as a temperature T1. You have a Carnot engine. Carnot engine is denoted by C. Okay, and this, it is accepting some amount of heat Q1, it is rejecting some amount of heat Q2, and the final temperature is T2. Okay, so the efficiency depends on the difference in temperature. Okay, and if you can see, lower is T2, higher is T1, the efficiency is more. Okay, so the efficiency depends on the difference in the temperature. If you can take this temperature, lower temperature, as low as possible, okay, and if you can increase this higher temperature as high as possible, the efficiency of Carnot engine increases. Okay, so all, as I said, all the engines that we work is basically a modified version of Carnot engine, a inferior version of Carnot engine, a local version of Carnot. You can say local version of Carnot engine, right? A Chinese version of Carnot engine. So if you have a good iPhone, okay, which costs about more than 1 lakh, and if you get an iPhone of iPhone look-alike which costs 10,000 rupees, you say this is the Chinese iPhone. Right, so all the engines that we are using in our day-to-day life, compared to Carnot engine, you can say that is a Chinese engine. Okay, even though the engines are not Chinese, most of them are manufactured in different parts, and 90% of them are manufactured in India as well. Okay, only if you import a car from outside, maybe it will have an engine manufactured outside. Otherwise, all the Indian manufactured car, they produce engines in India. Okay, so but that's just give you an example, that's just to give you an idea, okay, how inferior our engines are compared to Carnot engine. You can say they are Chinese engines, okay, that's it. Now in case of our day-to-day engines, okay, what are these two temperature sources? Okay, first of all, to operate an engine, what you require? You require a fuel, right? Petrol, diesel, CNG gas, right? To when you are operating a car, you need that fuel. That fuel, when burns inside the engine, it generates a temperature, high temperature, okay, that is the higher temperature that we are calling T1. Okay, whatever temperature is created inside the engine, that is T1, and whatever temperature surrounding us, okay, that is our sink. So whatever temperature produced inside the engine, that heat is being released to the environment, right? So environment is a huge sink, okay, it can absorb a lot of energy. So T2 is our environmental temperature. Okay, so this is basic. The two temperatures are required in our to operate an engine. So we have natural sources for these two temperatures. So this is temperature T1, which is the temperature generated inside the engine. T2 is the temperature of the surrounding. Okay, so this is the efficiency of a Carnot engine. Now in terms of heat absorbed and heat released, the efficiency is given by eta equals to 1 minus Q2 by Q1. Okay, in terms of this is the amount of heat released, this is the amount of heat absorbed. Okay, this is also another form of efficiency of Carnot engine. Now if you see, both of them are efficiencies, right? So what you can say, we can say 1 minus T2 by T1 is equal to 1 minus Q2 by Q1, right? Or you can say this is cancelled, so you can say T2 by T1 equals to Q2 by Q1. This is an important relationship to remember. You can remember this relationship, or you can remember these two relationships. Both are fine, but if you remember this relationship, sometimes it will save some 10 seconds of time, because sometimes some questions comes from this concept as well. So efficiency is fine, but sometimes they will not ask you directly efficiency. They will give you a question where the question will be based on this formula directly. Let's see one such question which came in 2018. A Carnot engine takes 300 calories of heat from a source at 500 Kelvin and rejects 150 calories of heat to the sink. Okay, so we have a Carnot engine. Okay, the temperature of the source is 500 Kelvin. Okay, and it says that it absorbs 300 calories from the source and it rejects 150 calories to the sink. The temperature of the sink, say T2. Okay, and the question says the temperature of the sink is, okay, so you do not need to use the Carnot efficiency of the Carnot engine equation. We can directly say that we know that Q2 by Q1 equals to T2 by T1. Okay, so what is Q2 here? Q2 is 150. Just you have to remember that whatever is related to sink is 2, whatever is related to source is 1. Okay, so Q1 is source, 300 calorie. Now here you see you do not need to convert it into joules as well, because this is simply a ratio. So even though the values are given in calories, you don't need to wait, you don't need to convert it into joules, that is the SI unit. You can simply do it by saying, okay, everything is calorie. So what? This is a ratio. So you can cancel 1 by 2. So T2 is 500 by 2, so it will be 250 calorie. Now remember that the value of sink should be smaller than that of the source. Very, very important. Okay, so these two options, in case you are guessing, okay, in case you are guessing, you should remember that temperature of sink should be less than that of the source. So option B, C and D are automatically gone. Okay, so you can either guess this, but if you know the formula, if you calculate it, then you realize this is 250K only, right? I hope you enjoyed today's lecture. Okay, all the lectures that we are doing is available in a single playlist in our channel. For that you have to join our channel. Okay, subscribe to our channel, YouTube channel, and join our WhatsApp channel. WhatsApp channel is different, where you get updates, okay, all the information related to KCET exam schedule, related to whenever we are doing a new series. Okay, everything you can get in our WhatsApp channel. Okay, link is given in the description. And obviously you can bookmark this playlist any time of the day. If you want, you can check from this playlist as well. Okay, I hope you enjoyed, and I wish you all the best for your KCET preparation. And anyone who is preparing for KCET exam, please share this video with him or her, and ask them to subscribe to our channel. And if you like this lecture, don't forget to leave it comment and like it. I will be back with the PYQs tomorrow. Till then, bye.